Hi, my name is Eric Munson. With Larry, we're going to talk a little bit about the Unikernel Advantages project and how we apply a general purpose operating system from Unikernel Optimizations to general purpose.
Yeah, getting very well.
All right, let's try this one. Is that better? I think yeah. I'll go with this. I'll try that first. All right, great. So first, we're going to talk a little bit about what is a general purpose operating system. So we've had decades of work in engineering work and research work set up to ensure that we had process isolation so that multiple people, multiple untrusted entities even, could run applications on a single operating system. And we come up with a diagram that looks something like this. We have two users, processes that are running. They're both running on the same kernel. The kernel has a lot of infrastructure built into it to isolate these processes and to ensure that they can't interfere with each other. But it's not quite that simple. Modern deployments actually do something more like this, where you have every process, every user has their own deployment of an operating system that lives on top of a virtualization layer with another operating system or hypervisor underneath, right? So we have all of this infrastructure built into our general purpose operating system to enforce isolation that we're not actually really using, right? You don't have multiple untrusting users using Ren on the same kernel. That's not really a thing we do anymore. Right, so with this notion comes the idea that, well, we really need to pay for this anymore. We really need to have this general purpose operating system. And so there are the idea of a Unikernel or a library operating system is sort of taking on some interest, right? And so what this is when you take the bits of the operating system that an application needs and divide them into a single binary with the user's application, and then you run that just as its own operating system. Right, and so there's a number of different projects that approach this, right? Starting with clean slate implementations, which don't harvest any code from working operating systems. They start from scratch and re-implement everything, right? Great idea to provide you with exactly what you need and only what you need, but maybe this would be a little bit tricky if you aren't an operating system developer yourself, and if you need something that the library doesn't already do, okay? And you can see there's examples. Mirage, FRP, Artifacts, Unicraft, a number of operating systems out there that take this approach. You also have systems that sort of try to split this. So you'll have some reused kernel code that lived out specifically the Arch-independent kernel code into the library and provide that to the application and trying to minimize what the actual underlying operating system is actually doing. In this case, platform support and hardware support, and that's it, right? So we're sort of discussing here what it means to be an operating system and where all of this code lives across a separation in privilege. And finally, you have systems that are incremental, which don't require a whole lot of new code, but they also don't provide the same level of flexibility that a full implementation would provide you. So you have a standard operating system with all of the entry and exit points that you're used to. But in this case, you take a process and you move it into a more privileged layer. So it has some more access, some faster access to the operating system, but you don't provide a whole lot of extra flexibility with this. Okay, so we talked a little bit about Unikernel Advantage. Let's be a little bit more explicit about that, right? So one of the things that you're provided here is that you don't have the same overhead from system calls because you're not transiting a protection boundary anymore. That protection boundary doesn't exist if you're right? You don't actually have process isolation because we don't necessarily have the notion of a process, and we certainly don't have the notion of a process from which we need to be protected, right? And you don't have a schedule anymore. We don't have processes. We don't need a scheduler, so we just run whatever the application we're supposed to be running is. You get significantly improved things like boot time, and because you do jobs like hardware bring up, you offload that to the hypervisor. One of the things about requiring virtualization is now you no longer have to care about every potential network part or every potential disk controller you could be using. That's just going to be handled by the hypervisor, and we're not going to worry about Arch-independent code. And finally, you can really strip your image down so that it only contains the code that you need, right? Both in your user application and in your operating system, which can lead to significantly smaller images, which also contributes to faster boot times. But, and this is the big part, most of these Unikernel systems we talk about, aside from the incremental systems, they don't provide Linux or even POSIX compatibility. They don't guarantee any of this. Often they will give you some wishy-washy terms about we support maybe 20% or 30% or 80% of the POSIX API, but even if they support that API, they don't have any of the implementation quirks that your application might be relying on from a specific POSIX implementation. Rewriting your code for an operating system with an API that you're not familiar with can be really tricky, even more so if you don't have niceties like really abstract memory management or process scheduling or any of the things that you rely on generalized operating systems to provide to you. If you don't have those, now you're responsible for writing them. You don't have the depth of understanding, it's tricky. It can be really hard to debug at both performance and correctness in a system that doesn't support things like processing, right? How do you have GDP code running with your application if there is no notion of a process? Okay. You also, for most of these systems, especially the full implementations, they require virtualization. This is not an option. You can't boot it bare metal. You have to boot it on top of a hypervisor. And that may not be what your application wants. You may not want to pay virtualization overhead for this. And finally, all of these clean slate implementations, they are a clean slate implementation. There's not the processor years or decades even of a system like Linux that has been running in production for decades on CPUs. And we understand how to debug it, we understand where performance bottlenecks lie in the system. But with many of these clean slates, it's all brand new. So let's talk a little bit about what the UKL project did. So our notion was, we want the ability to apply Unikernel optimizations to a system, but we don't necessarily want to have to rewrite everything. In fact, we want to provide a developer with the ability to take the application that they have in user space, modify it, no code at all, simply rebuild and relink, and now you are running inside the kernel, right? And that's exactly what we provide. This is sort of an illustration of what that is, right? You'll notice that we have the same sort of picture that we had, including support for user space processes in the system as well. But now we have an added node over here on the left that is the UKL process, which uses the same entry and exit points that a standard user space process does to interact with the kernel. These are just now function calls as opposed to system calls. So that opens up the potential of some really interesting optimizations. These four are the main four that we explore in the paper. However, because of time today, we're only going to talk about one, which is allowing the application to directly interact with kernel services without having to go through the standard system call interface. So to give a bit of a concreteness to that, what we have here, we show the three different models and the entry-exit points that are used by the various UKL implementations. So from the previous slide, you saw that the base model up there, it talks to the entry-exit code for the standard kernel system calls. We have a model that bypasses some of that, but leaves in all of the disambiguation that is done in the virtual file system layer for the Linux kernel. But finally, if you really know your application and you know that it's not going to need that disambiguation, you can reach directly into the networking stack, say, and call the TCP functions that are needed directly. Let's see some results of actually working with this. So what we have here are the probability distributions of the latencies on calls to a Redis server. This one is runs standard process in the Linux user space, right? The key things you need to pay attention to here are the two vertical bars, the red and the purple ones. These are the P50 latency and the P99 latency. And we'll see how they change as we apply some of these optimizations. With simple bypass, that is, skipping the entry-exit code and going directly to the kernel disambiguation for read and write, we get about 10% on both P50 and P90, right? So we've moved both bars to the left and we squeeze them a little bit together. So it's a little bit tighter. But the real key here is when we call the TCP layer directly, we get a huge savings. We see 23% better on P50 and 22% better on P99 latencies, just by allowing a user process to interact directly with the underlying networking hardware. Cool. Thanks for coming to the presentation. So the paper will be available with URSys 2023, and there's a poster session out at the first poster segment here if you want to come have a deeper look.